So, injecting reliability into generative AI. What does this really mean? Am I saying that generative AI is unreliable? That's not really what I want to say today. It's more that it's not reliable by design. Okay? I want to get into how we can accomplish this, inject some reliability by using tools like computational tools like Wolfram Language, equipping large language models, for example, with the power to execute reliable and robust computation. So there will be code examples, there will be kind of me telling a story about this notion of statistical AI versus symbolic AI, where a large language model, for example, I would define as a statistical AI because it's using, statistical processes to make an informed decision of what the next word should be in a sequence of words. And symbolic AI being more like something like Wolfram Language, where it's very strict rules that execute, computational steps. And as always with these webinars, I'm never too sure of the familiarity of the audience with Wolfram Language, but I am presenting this webinar using a Wolfram notebook, okay, in which I can execute Wolfram Language code. So as an example, here's 2 + 2 = 4. I could also plot the sine of x as x goes from 0 to 10. Okay, so yes, we're in this computational notebook environment, and we're going to talk about injecting reliability into generative AI. So let's talk about some of the reasons we might use generative AI. So like large language models, for example. And if you think about how you yourself use these tools, I'm happy to hear more about how you guys use LLMs in the chat. If you want to, discuss this, that would be great. But the answers you get back are typically, the answer that follows a question you have, some kind of explanation that follows a statement that you make, or maybe it's more like a response that follows an instruction. Okay, so maybe you ask, I don't know, something about which travel documents do I need if I'm traveling to the United States? Or explain to me how the divergence theorem works in electromagnetism, something like that. Or maybe it's summarize this in 50 words, or write me a interesting summary of this long blog post. Yeah, so I'm sure you're all, those of you who've used large language models, this is kind of familiar to you. Whereas with symbolic AI, we have defined rules of behavior for structured inputs. Okay, so, I know the syntax when I'm writing Wolfram language code, and I know how this is, processed by the Wolfram kernel and then converted to a kind of low-level language, and eventually we get our output, whether it's something like 2 + 2 = 4, or whether it's a plot of sine of x. Okay, and these are kind of at odds with one another, these two AIs. You could call it a tale of two AIs. So you have this statistical AI and symbolic AI. Each have their strengths and weaknesses. And then here's a couple of examples of kind of this raw computation that we enjoy with Wolfram language. So this is a nice kind of click-through interface, really. Those of you who aren't as familiar with what we do here at Wolfram, this is very useful to you. So we can do machine learning. Okay, you can build neural networks. You can do image processing. This is a kind of feature space plot of pictures of dogs. You can check the success rate of a classifier with a confusion matrix. You can train a neural network, that kind of thing. You can do statistics and make all these nice visualizations based on your data. We can also work with geographic data. Here's a multitude of different geographic plots and geo-elevation plots. This is the geo-elevation around the city of Edinburgh, which is quite nice. You can plot vectors on top of maps. You can even use different, what's the word? Projections for your maps. Okay, these are computational rules. A map projection, I'm going to stick with this example like this. I don't exactly know which projection this is, but it's a well-defined thing. It's something you can compute, so you can go from one projection to another because you know the rules. And with Wolfram Language, it's quite easy to do that because of all of the built-in knowledge we have. Okay, graphs and networks. So if you have some data that is best visualized with, nodes and edges, as is often the case, you can do that. You might also have like algorithms on top of this structure, like a find shortest path or the traveling salesman problem, that kind of thing. You can work with time series, do different kinds of optimization, work with audio and video. Each needs their own rules, Each has a different file format that you need a way of handling. You can do text analysis. And this is kind of getting to a bit closer to what large language models are doing, I suppose. They are abstracting away the rules behind language and if large language models have told us one thing, it's that the patterns of our speech is somewhat easy to pick up if you have a big enough model. Okay, we have the other categories of Wolfram language like chemistry, astronomy, biology, and then engineering, model-based systems engineering, that kind of thing. And then recently, we have our AI integration, which I'll talk about, and some educational technologies too. So that's a whistle-stop tour. Any questions on this, feel free to just stop me and I will decide whether it's worth answering now or whether I'll leave it until the end. So let's compare pros and cons of symbolic AI and statistical AI, okay? Here we've got a relatively high-level look at things in a table where we're saying, where does computation thrive? Where is it really good? And where are LLMs really good? And as you can see, they kind of complement each other here. So logical thinking, following complex rules, using large data and reliability. I think it's fair to say that the sensible choice is to go with a reliable form of computation. Computing the digits of pi, for example, like I know every year we discover a new couple billion digits of pi or something like that, and it wouldn't be something you'd ask a large language model. Okay. However, with the advantages of a large language model, we can give it a wide range of inputs. Okay. Think about the amount of users that something like ChatGPT has. Each user is interacting with the product in a different way because each user asks questions differently. So you have this wide range of inputs that this large language model can accept. Whereas something like Wolfram language or any programming language, the syntax has to be correct. You can make a spelling error and a large language model will kind of infer probably what you meant from that if it's not too bad. It also has this appearance of human-like interaction, which is convenient for people. It feels like they can, they've got a nice feedback there where it's like a supportive friend in some ways, telling you what you need to know if you're doing research on a topic. It's almost like studying with a friend, except that friend knows a lot. Now, I should say here that this human-like interaction has caused some problems, like people using a large language model as a kind of therapist, or people falling in love with the large language model. And these are perhaps unforeseen things to have happened. Okay, large language models can also work with poorly defined fields and unstructured data. So if you had all of these bases covered, that kind of means that you need a union of computation with LLMs. And that's exactly what I want to talk about today. Taking what I said earlier about the areas in which large language models are a bit weaker, we can start to look at some examples. And this is an example from a long time ago. As you can see, the ChatGPT interface here is a little bit different to how it looks now. And this was someone who gave this talk before I did. And they wanted to find out, basically, could LLMs kind of deduce things from like some non-trivial piece of information that you give it. So here we have, if Alice is older than Bob, Bob is older than Charlie, and Charlie is younger than Derek, is Alice older than Derek? And then this particular model, I think it was a couple of years ago, essentially misinterpreted the prompt here and said, yes, it is true that Alice is older than Derek. But we can check with computation that it doesn't necessarily follow that Alice is older than Derek. Okay, and we've used kind of a very strict, rigorous definition using all of these operator symbols like greater than and, for all, using these Wolfram language functions like assuming and reduce. Okay, so this paints a nice picture of the difference of like asking this question to a LLM and asking this question to a computational language. But I asked this problem again to ChatGPT more recently, and as you can see, it gets it right. I think this is GPT-5. So you can even see the text here that says it thought for a couple of seconds. So this is one of the thinking models, or reasoning models, as it's sometimes called. So this is to paint the picture of the progression that these large language models are on. Okay, they're an incredible piece of technology. And even though this talk is essentially about how we can improve them, they are incredible. Okay, I think for, let's say, someone who has had a 30-year career in tech, not me, but some people I know, you might say that large language models are one of the biggest breakthrough that has happened since the internet, really. Yes, so it is an incredible piece of technology and getting so much better all of the time. This next example is a little bit more clear-cut about where something like ChatGPT just isn't the tool for this job. Okay, so I said, what is 3 to the power of 45? And what has ChatGPT done? It's broken the problem down. Okay, this looks like a perfectly reasonable thing. It knows its laws of indices, and then wants to compute these separately, and then do some summing up and cubing of the result, etc. So it's kind of told a story about how you'd work something like this out, and then we've got this result. And it says, wait, let me confirm, and then gives a different result, and then tells me this is its final answer. But if I use the Wolfram language to just work this out, we can see that we get a different answer. And, well, let me tell you, the Wolfram language result is the correct one. So ChatGPT has got this calculation wrong. And it's important to note, like, as I started this talk with, they are not built to do this sort of thing. They're not designed to do this sort of thing. They are large language models after all. So this model has kind of answered this question like a human would, where, if you had, if you put someone on the spot and said, what's 3 to the power of 45? You might just try and break it down and then make a kind of guess about how many digits you need after the leading digit and that kind of thing. But you're not getting the question right, which is important, okay? Especially as we become more and more reliant on these AI systems. If anyone has other examples of interesting cases where a large language model is to get something wrong, then feel free to put them in the Q&A or the chat on YouTube. I'm just going to choose now to turn my camera off to make sure the bandwidth is sufficient. So I want to move on to another example of a slight weakness of a large language model. Okay, and this is to do with reliability in its answers to questions. Okay. So I got this example from a colleague. There is a type of cactus that has all sorts of mineral levels in it, all sorts of minerals that it needs to extract from the ground in the desert. And we can ask this question: why does this saguaro cactus have unusually low potassium levels? Okay. And then we get this lovely answer of, why it has low potassium levels. Okay, this all seems reasonable. But then we can also ask in a separate kind of prompt why this same cactus has unusually high potassium levels. And then we get a kind of just as appropriate an answer for the opposite conclusion. And this is really quite interesting. It kind of ties into the problem of sycophancy when it comes to large language models, how they will, once you've said something, they'll take it to be the truth and kind of really encourage you and hype you up that, yes, you're right, let's get to the bottom of this and let's work on it together. And this is a well-known problem that the big AI companies are trying to fix. And again, back to these unforeseen circumstances, I mentioned people falling in love with their large language model. You also have examples of people who have been kind of driven into a bit of a mental delusion that they are Neo from the Matrix or something like that, or that they've invented some new kind of mathematics. So I should say that these examples were with web search off. And this is a really important distinction, because now with web search on, you're unlikely to run into this problem. But this web search, again, you can think of a kind of tool that is given to the large language models. It's not inherent in their design. But yes, if you had web searches on, it might be an interesting experiment to say like whether the large language model would actually contradict you and say, oh no, that's not the right question to ask. Okay, and we've got some strengths of the large language model here, of just some nice examples that I found. This human-like interaction. So we can ask ChatGPT to describe Wolfram Alpha in the language suitable for a 7-year-old, and we have this like this kind of new persona that it's taken on with a completely different way of speaking than it would to a adult, for example. We can give it a very short text like messy data gives no insights, computable data can be used better, and we can ask it to expand upon this in 100 words. Sometimes it doesn't just sometimes it doesn't respect that 100-word limit, but it always gets it roundabout correct. It would be interesting actually if I could use this text recognize function to see how many words it actually used. Just having to download some libraries first, but okay. So I could do like a string split of this string. And then find the length of this. Yeah, so 86 words it looks like, instead of 100. Anyway, that's a little aside, but something I quite thought it would be interesting to do. It's also, yeah. Okay, final example of my kind of little dive into my experiments with ChatGPT. How many dogs are mentioned in the following text? 2 basset hounds are walking down the street when they saw a Persian cat talking to a Labrador. Return only the final number. And it's been able to take this unstructured data, which is like a sentence, and then kind of extract anything that it knows to be a dog, and then obey my prompt that is returning only a final number, and there returns only the final number, which is great. Really useful for when you want to then do reliable computation on unstructured data. Okay, and we've got many talks that discuss how you can handle unstructured data and things like that. Now, some of you might know already that if you look in the GPTs section of ChatGPT, you will see that using Wolfram is actually one of the options. So we can use prompts like plot the intersection of x squared plus y squared is less than 1 and y is greater than x. And it will show us the code that you need to generate this. But then also, if I say, yes, I want you to run and show this code, it will make an API call to the Wolfram cloud and then actually show you the plot. So this is quite nice. This is kind of having the Wolfram language as a plugin to ChatGPT. So if you want very quick visualizations that you're familiar with the Wolfram language as a tool to visualize things or a tool to compute with, then this might be something that you use. And it is often called Wolfram GPT. And then here's a second example. I might ask, what are the populations of different livestock in Turkey, in the country Turkey? And the LLM will kind of give me a spiel about how it's going to use the entity in Wolfram language specified by Turkey and then kind of query it to find out its properties of livestock population. But kind of, I guess, somewhat frustratingly, it doesn't just give me the populations, it asks me a question to clarify. But, you know, after asking me that and I say, yes, I just want the most recent ones of cattle, sheep, goats, chickens, etc. And then it will find that information. And then I just need a follow-up prompt where I say, make a bar chart for 2020 only. And then we have this bar chart, which is nice. I mean, you're kind of just uttering what you want in natural language, and you're getting a perfectly reasonable bar chart in response. And it's also included the data again below it using these emojis. I know some people don't like ChatGPT's use of emojis, but yeah, here we are. Okay, so that's kind of Wolfram as a plugin to an LLM. You might also be interested in LLMs as a kind of plugin to Wolfram. So this kind of introduces us to the whole world of Wolfram language LLM functions. So we have LLM function itself, we have LLM prompt, LLM tool, LLM synthesize. LLM synthesize is probably the easiest one to introduce, where it's just kind of it's just a chat interface, really. It's taking your prompt and finishing off what it thinks the prompt should be. There you go. It got that the next word is typically Matt, and then it kind of told us a nice story about what this cat happens to be doing. Okay, but LLM function is really useful if you want to be a bit more programmatic with your use of large language models. So here, what I'm doing, I'm just going to delete this cell. I have set up this LLM function, which is to write a parameter summary of second parameter, share price, yesterday, given the following facts, third parameter. Okay. So this is the definition of a variable I've called finance story, which takes 3 parameters. Okay, those parameters are going to be, well, we haven't explicitly had to say what they're going to be, but from context, the first parameter is going to be some kind of descriptive word about the story we want to tell. 2 is going to be the company whose share price about which we want to tell the story. And 3 is going to be the actual stock price information of that company. So this is kind of how this is going to go. We're going to make a text cell where this is our finance story function, which needs 3 parameters. This is the first one, where we're saying we want a random choice of exciting, optimistic, or pessimistic. And I'm just using this echo function so we know which choice it actually finds. And @ is just a shorthand for applying a function. Okay, Microsoft is going to be the company, and this association, which I can put in a new cell, is going to be the facts. So this is the opening price, the daily high, daily low, closing price, and volume of the Microsoft stock, I believe, today. I guess yesterday, because yes, we won't be getting live prices using this financial data, but financial data is essentially what queries, I think, a Yahoo database for stock prices. Anyway, so this is what we need. We'll run it. So it's going to tell an exciting story, and then we're just, you see that little pop-up there. It says waiting for Wolfram LLM service. Now, it's important to know that this isn't Wolfram's own LLM. This is an external LLM that we are using through the product that is Wolfram LLM Kit, a notebook assistant, which I can actually put on screen. Now, it's also in the Offers tab if you're on Big Marker. Okay, anyway, so here's the result. I'll let you guys read this. So it's a clear example of, using the LLM's advantages of fluency and being able to kind of tell a story like a human, but equipping it with these facts, like, what did the stock actually open at? What was its high? What was its low? And what was its finish? And obviously it's taking this exciting prompt very literally, with things like staggering volume, palpable, keeping traders on the edge of their seats, that kind of thing. Cool. So that's a very nice example. It's simple enough, but we've established how we can. This LLM function is essentially behaving like any other function, like a function f of a, b, and c. If I wanted to define this normally in Wolfram Language, okay, you can kind of see how this LLM function is working exactly like a normal function. It's almost easier because you just need, the way that this LLM function works is that it's kind of like a string template. So underneath it's just, it's essentially one of these. Where you just have slots that are taken up by your parameters. Okay. So another example here, we're going to use another one of Wolfram's tools. So we saw LLM synthesize earlier, and this is a kind of more complicated version of LLM synthesize, where we're going to give it an LLM evaluator. So this is the prompt: write a short paragraph comparing Chicago and New York. Use the tool provided. So we're giving it an extra hint to use this tool. And then the LLM evaluator is an option to LLM synthesize, where essentially the value of this option is an association where the tool's key goes to a value which is an LLM tool. This first argument to LLM tool is just the name of the tool and then what that tool does. We have a kind of a parameter of like how to interpret the parameters that this LLM tool takes. So the parameter is a city, and we're kind of telling the tool to interpret it as a city in Wolfram language, and then we're going to use the population property of that city, just like how in Wolfram language, you can take a city like New York and then ask for its area or its or property crime rate. Okay, so very simple again, but this is the result. So we're going to run this, and then we get a short paragraph comparing Chicago and New York, and we've enabled it to use the tool which queries the population. So we can actually get this information. Maybe the large language model that is being used here would have some idea of this anyway, because it's been trained on data where it mentions this, but this at least equips it with a way to get it reliably. Okay, here's a slightly different example that uses an API indirectly, but still uses the API nonetheless. So here we are setting up the LLM Evaluator Association by saying that the tools now has access to an LLM tool which finds information about a postcode. Okay, here in the UK, we use postcodes to identify locations, and a colleague of mine has written this function which takes a postcode and returns all sorts of useful information about that postcode. It's a resource function which you can access on the Wolfram function repository, shown here, called UK postcode lookup. Okay, so this is essentially the tool we're going to be using. And inside that resource function is a call to an API, basically. So here's just an example of us running this resource function on the postcode of our UK office. And then we have all sorts of information like, okay, where actually is this? What region is it? What is the parliamentary constituency? What's the administration district? What's the parish, etc., etc. Okay, so now we can ask questions to the LLM like, what constituency is this? Giving it our LLM options, and then we get correct answers back. And you can see even in that pop-up there, it says it's using the tool. So the constituency is Bicester and Woodstock, and there you go. Okay, we can do the same for the parish. We're expecting Hanborough, and we got it. Okay, here's an kind of a bit more of a computational example. Yes, we can ask for the coordinates, returning only the coordinates in the form geoposition, latitude, longitude. Interesting, and no other words. So this is a little bit contrived, I will say, because we're asking for it in this form, geoposition, lat, long, because eventually we use to expression of it, and this, what is returned here is a string, I think. Yeah. Whereas this is a geoposition, and we've kind of used to expression, very useful function, to go from a string to a useful Wolfram language expression, which is a geoposition here. So yeah, it's fine. Sometimes you have to, be very strict on what you want your data to look like. But then what's really useful here is that we can take this position and then plot it on a map with a geo range, so you can actually see the surrounding area to our UK office, where I am presenting this from right now. And it's also worth mentioning that new in 14.3, the geographics are a lot sharper. So we're kind of using vector graphics here instead of what we were using before. Okay, and then here's just a very quick numeric evaluation tool where we're kind of looking in the prompt for some code and then converting it to an expression, and then kind of returning the result. So yeah, this is essentially just doing to expression on 3 to the 45, which gets you your long answer. And because of the way we've asked for this, we kind of have some formatting that isn't typical of a LLM response. But yeah, you'd be able to configure this as you like it. Okay, so I don't have too many slides left, but these final slides contain kind of more of the like where you can really take this once you're happy with your combination of unstructured data and like tasks you want to give to your large language model, for example. So in this simple example, I've defined this variable a name age height extractor, okay, which is using LLM example function, which is a really useful function where you need to give it a few examples known as few shot examples or one shot examples, where it actually creates an LLM function based on those examples. So here's my kind of input data here. I just have a sentence. John is a 52-year-old male who is 6 feet tall. And the output is an association where name goes to John, age goes to a quantity which is 52 years, and height goes to a quantity that's 6 feet. Okay? Then we have a second example where the name is there, the age is missing, but the height is there. Okay? And then we have an actual sentence which gives information about two people, and we have a list of associations, of two associations instead of just one. So with this very little information, we're kind of telling the LLM what we want as a result of kind of looking at this unstructured data. Okay, so I'll define that and then run that. Well, I'll show you what it looks like without being run on anything. It's a LLM function where this is the kind of content. Okay, we're going to run that on this sentence. One day I met John Smith. I couldn't believe he was nearly 70. His wife, Kate, is surprisingly tall. Should be surprisingly tall. Perhaps 6 feet. His son, Mike, is only 3 foot, but that is because he is 2. Okay, and let's see what we get. So we have a list of associations where the name goes to John Smith, age is 70, height 6 feet. New association, name Kate, age missing, height 6 feet. Mike, age 2 years, height 3 feet. So, interestingly, there's a mistake here where it has assumed that John Smith's height is 6 feet, even though that was not mentioned. Okay? So this should really be empty or missing. But, you know, I think it's a pretty good result for a short, simple, instructive example of getting a structured data set from an unstructured input. And we see more and more clients who want to, use Wolfram Technical Services. This is what they want to do. They have all of these documents and things like that, but they also have, strict standards to follow and rules to follow, and it's taking their employees lots of time to kind of comb through documents and see where things have changed and that kind of thing. And this is really where you can harness the power of AI hooked up to reliable computation. And here's a really nice case study of this. This was actually this was carried out by 2 interns we had here at Wolfram. And I'll give you a brief summary of it, but I really encourage you to read this yourself. Is that when when someone unfortunately dies, there is something called a coroner report, and there's always an investigation into the a potential cause of death. And then in some cases, you might have a reason why this death might have been prevented. Okay, and these take the form of these forms that you have to fill out, called a prevention of future deaths form, which are very well structured forms. Okay, there's clear input fields that you have to input. But that input is unstructured data. Excuse me. It takes the form of the coroner or whoever is filling out this form is, in their own words, just saying what has gone wrong, what's happened, etc., etc. So using a large language model, our interns were able to categorize the input field into these different categories that were well known from literature, and actually automate the process of this investigation into prevention of future deaths. So this essentially was a proof of being able to conduct research like this in an automated way. Therefore, it saves researchers so much time, and the researcher is more focused on, okay, what do I do with this conclusion, rather than manually combing through all of the unstructured data by hand and making a judgment of which category it goes in. Now, obviously, you don't want to just give everything up to the AI and say, and not have any checking of the categories it put things in, but there are guardrails you can put in place for that. And this is a very nice read, and you have this some of the data lends itself to being visualized in a timeline plot, and this is all done using Wolfram Language, so it's a very nice use case. Okay, next example, we have content correction. So again, we're using a similar thing to above here with LLM example function, where we're going to correct errors in automatic speech recognition transcriptions about human medical topics. Okay, so some transcription softwares get things wrong, but if you can contextualize it and you know what you're talking about, you can probably infer the mistake. So here the topic was eyes, and the transcription has picked up, I have cats and glad aroma. I'll let you guess what the output you think will be here, but based on these 2 examples alone, the LLM function has identified, and the LLM call has said, you know what, this probably means cataracts and glaucoma, which are 2 relevant what would you call them? Diagnoses for opticians. Yeah, and this is a similar example of just making sure to prescribe the right medicine and things like that. And yeah, obviously, if you were in the medical field, you'd put a lot more care into which drugs you prescribe people than just asking an LLM. But this example is just to show that, based on the training data that this LLM has, it knows which conditions different drugs are associated with. Okay, here's a nice kind of computational example. So we have convert the drug name into the purpose of the drug and return a single word summary. So I can run this function on, let's say, aspirin. Okay, and it says it's an analgesic, but then I can also map the function over a list of these drugs and then make a pie chart of the result. And as you can see, it's this is quite interesting because it's called two of them the exact same, but one of these has a full stop and one of them doesn't. So when you've done counts of this, it's identified 3 independent results. So this is kind of an interesting thing where like the LLM needs a bit of wrangling here because we've said return a single word summary, and it's essentially returned like a word and a full stop, which is kind of annoying. And this is the perfect illustration of how things can go wrong. Okay, so now we have a second attempt because, as I said before, these large language models are statistical AIs. Not every iteration is the same. There we go. So even though that was kind of unintended behavior, I'm glad that it happened because it was a nice illustration of what can go wrong. Okay, and then we have another kind of interesting example here where we're plotting the list of countries where people believe in ghosts on a map. And I'm sure there are people in every country that believe in some sort of ghosts, but I believe this is just the LLM's assessment of, on the whole, which countries believe in ghosts. And then we're going to plot them in red and a polygon around that country. Interesting. Yeah, so according to this large language model, if you live in Australia, apparently you don't believe in ghosts. But we do here in the UK, apparently. Okay, moving on to one of the new features in version 14.3 is LLM graph. So this is quite an interesting function which kind of extends the normal chat interface of like prompt response into more of a graph structure. So if I show the documentation of this LLM graph with an association of name goes to fun, we have an LLM graph where the node specified by name evaluates this function, which is often a prompt, on the node's outputs. Okay, so that will make sense after this example. So here I'm creating 3 nodes. One is poet 1, poet 2, and judge. And I'm asking poet 1 to write a short poem about summer, poem 2 to write a haiku about winter, and then the judge to actually choose the best poem among those 2 poems that have already been generated in this same LLM graph, and then copy it. Okay, so we're going to run this, and then we have our best poem function. So we can just run this with no arguments. We can see that it's computing the nodes, and then it's judging based on these nodes. And even though we haven't seen poem 2 here, this has happened in the workflow, and the judge has gone with poem 1. And it's also given a reason for why it's chosen this poem. And here it is. And we can go a bit deeper and say, like, we can find the information on this function. This doesn't really like tell us any more than it doesn't tell us about why it made the decision or anything like that, but it tells us, it shows us the structure and kind of our output names. Okay, I'm gonna yeah, this is interesting because this function was a prompt, right? It called an LLM and wrote a poem. But here I'm actually going to just run this function using my own inputs. Okay, so I'm going to I've made up two poems here. The first one is "The cat sat on the mat," and then the second one is the first stanza of a very famous poem. I'll be very impressed if anyone in the audience can put it in the comments and tell me which one it is, and I will make sure you get some prize. Okay, but here we go. So all we need is the judge now, and the judge is going to rank or choose its favorite out of these two, and it chose the best one in its opinion, and then copied it here. I'm just wondering why it didn't copy the whole thing. Anyway, so that's a very basic intro to LLM graph, and this is a bit of a more complicated example where you might be able to correct a workflow in like a piece of mathematical calculation or something like that. So we have the decide node, which decides if anything contains errors, and we have an input here that this needs review, lists the errors, but this review is dependent on there being any errors in the first place, right? Because you don't need to list any errors if there aren't any. Rewrite is rewriting the input to fix any issues, so it's kind of going to correct it. And then the final is is checking that if there is something that we have to rewrite, so like if rewrite is itself a string, we will give the incorrect input and then the correct input of how it's been rewritten. Okay, so here's the visual graph of what that looks like. So we have the input, it goes to the decide node, which goes to the review node, but yeah, so kind of ingrained in this decision is the kind of if statements that this LLM graph is using. Okay, so we can just very easily test this out. So in this, there are no errors, so it just returns it as it was. But in this, there's clearly an error, so it will identify the error and then rewrite it in the correct form. I also want to draw your attention to this new function, semantic ranking, also new in version 14.3, where you can sort items by their semantic similarity to something else. Okay, so this example in the documentation, I mean, I always come back to it just because it's the easiest to introduce this sort of thing. We have we have this list of things, and we want the semantic ranking of these with respect to the word fish. Okay, so tuna is considered to be the closest thing, and then shark, then whale, and then clearly we're into things that aren't fish, so they get a lower ranking. And then you can actually query this for relevance and that kind of thing. And this might seem a bit trivial and contrived, but then if you start to go down the documentation, you might see some real obvious applications, like if you've had a query, but which FAQ is closest to your query, and then you have like a recommended list of frequently asked questions. There's also this option called re-ranking method, which kind of tells you how you want to rank the actual things that are returned by semantic ranking. Okay, so this next slide is really just for me to show off our more complete, I suppose, like less programmatic AI LLM integration. So you can use chat notebooks, for example. So if I'll just exit full screen for a second, and I can do file, new, chat notebook, I get a new notebook where the default cell is a chat cell. Okay, so I can just interact with this like I would any large language model, and I have hopefully a response which tells me, how to plot sine of x in the Wolfram language code that will get me there. Okay, this is very nice. And you can obviously ask more complicated questions like, or commands like, how do I make this interactive? And it has knowledge of the prompt above it, okay? So here it's going to suggest to use the manipulate function, which is a very nice visual here, where we have this slider which represents k, this multiplying factor inside the sine of x. One important thing to say is that you can also add these chat delimiters, which is actually all you need is the tilde. You just essentially type one of these characters into a new cell, and then if I say, what did I just ask you? Because I've put this here, I'm essentially blocking the LLM from seeing anything. Okay, so that this might even be from a previous session. So it doesn't know that I just asked it about the sine function. Okay, so we have, yes, chat notebooks. We also have the notebook assistant, which comes with the LLM kit that I showed in the offer earlier. So we can just press this, and then we have this kind of similar thing, but a different kind of interface and access to a couple more features. Like this has access to the function repository, for example. So I can have a prompt like, how do I an egg box surface? And as you can see here, that we have a focus where we can see what the notebook assistant is currently focusing on, and it's focusing on my empty untitled notebook here. So I can just copy this, paste it in here, run it, and we should have a nice kind of parametric plot of an egg box here, which is very nice. Yeah, I like the notebook assistant. It does a lot of things very well. I'd encourage you to try it out. And this was the graphic I showed on the first slide. And hopefully now it means a little bit more to you, right? Combining the fluency and the human-like interaction and the ability to process unstructured data of LLMs with the reliable, robust computation that comes with Wolfram Language, you've enabled fluency and accuracy. And this is kind of a graphic of just depicting what that looks like. So you have the text user input going to a chat LLM here, but then also going to a kind of, I suppose, a Wolfram kernel, which carries out structured queries, might even have a symbolic representation of things like for example, an entity that is a city which has a population. Or you may even connect this to some enterprise data. So, some data needs to be private, and you don't necessarily want to give all of your company's data to something like a large language model. So you need this to all operate within your company's firewall or something like that. And yes, we've had great success with this so far. And whilst I think generally the claim that the brain is split into two parts that each carry out separate tasks has somewhat been debunked. It's a nice way to kind of imagine what's going on here, where you have ChatGPT, which is like the creative, almost flamboyant side of your brain, which doesn't want to work out 3 to the 45. It wants to tell you a story about how to work it out. Whereas Wolfram is a more kind of structured, rule following, computational side of your brain. And, together, these two things can be very powerful. Okay, this is my final slide. So I will just go through the questions that have been asked so far. So Paul Erickson said that GPT-5 answered 3 to the 45 correct without all the text, but the source indicated that it forwarded the question to Python. So, yeah, really, thank you for saying that. So, essentially, that's exactly what I've been advocating for, right? Hooking up the large language model to reliable computational tools. And it looks like OpenAI are kind of doing this with NumPy or SymPy or things like that, at least with some of their models, which is good. I mean, it shows that the large language model on its own isn't really supposed to be doing integrals or like solving differential equations or things like that. It's fascinating to see, at least with the new generation, of which I consider myself to be part of seeing an integral that's complicated and then just being like, well, I think I just ask a ChatGPT. And that's fascinating because that's really not what ChatGPT is for. And something like Wolfram Alpha, which is, which is incredibly good at solving integrals and still should be your go-to for solving integrals. So I just say integrate x. There we go. Case in point. If you want an analytical solution to an integral, then Wolfram Alpha is the place to go. But because these large language models are showing some success at kind of encapsulating what it means to solve an integral, because it's just had access to so many web pages where you have these step-by-step processes, that people almost think that that's the new tool. But I would just exercise a bit of caution on that front for now. So Jörg says, can you show how to get an API key? I'm actually using Wolfram's LLM kit here, so I didn't need an API key. So you should either check out the offer to the Notebook Assistant and LLM kit, or you should go via the model you want to use. So here, if I go Notebook Chat Settings and Models, then I can kind of pick a model that I want. And I'll need to connect these services. So here for OpenAI, I can choose one of these models, but then I'd need to set up an API key with OpenAI. So yeah, that's something you have to do on the LLM of your choice side of things. Malcolm said, when I use the question mark to find all these functions that start with LLM, that's right. But I could have also used names. Just you get them in a slightly different format. So yeah, absolutely. Very useful function to know. Okay, and then we have Elliot on YouTube saying, AI's merging with Wolfram is just a necessity. Yes, I think so. Merging AI with the most powerful mathematical software is huge. That is necessary step for AGI and artificial superintelligence. Next obvious step is to find a way to add the quantum computers into the mix. Okay, I like where you're going with that.